let's continue talking about right triangle similarity, and we need to throw a definition in here before we can use what we know about these triangle proportions to find some missing sides. So there's this concept in geometry called the geometric mean. And so the geometric mean shows up a lot in geometry in a lot of different places where this same value, right, this x value shows up in the problem twice, right? And so we would call that value, those x's, the geometric mean, okay, of the other two sides. So we're saying a and b, if I use those as my input values, then I'm going to be able to calculate a geometric mean. So let's see this in practice, and that will make a lot more sense than just using the algebra. So if I just say, what is the geometric mean of 6 and 15, and we're going to leave our answer in simplest radical form because we do not like decimals unless we have to use them, right? So they're going to say in this problem that the geometric mean, right, if you remember we said extremes are like these two downhill quantities, and the means are the two uphill quantities. So when they're talking about geometric mean, they're saying we don't know that. They're saying what is the mean, right? So in both of the mean spots, it's going to be the same value. That's the big concept here. Geometric mean, the same number shows up in both of the mean locations. And then the extremes for my proportion are going to be the 6 and the 15. And so if you notice, what I just set up is a problem that is pretty easy to solve. If I cross multiply the means together, I get x squared, right? And if I cross multiply my extremes, I get 90. And so x is really equal to the square root of 90, which we can simplify this radical. It has a square root of 9 in 90, and so I can simplify this down to 3 square root of 10. Right? So I would say the geometric mean of 6 and 15 is 3 square root of 10. Right? So if we want to see one more example, we could do the same thing with 4 and 18. Right? We could say, let's set up our fraction. Okay, we're going to say fraction equals fraction, which we call proportions, right? And we are going to set up the x values on the means, okay? And we're going to set up the numbers that we want to know the geometric mean of. Those are going to go right there, right? So we're going to say, okay, x times x, well, that's x squared, right? 4 times 18 is 72. So I'm going to say x squared equals 72. Okay, so that means that if I square root both sides, x is equal to the square root of 72. And the square root of 72, if you simplify it, there's a 36, which is a nice perfect square in 72. So I'm going to say, not the square root of 6. Okay, it's just going to be regular old 6 square root of 2, right? The square root of 36 is 6, okay, square root of 2. Right, so we're going to say, in this case, that the geometric mean of 4 and 18 is 6 square root of 2. Right, so let's take a look and use this now. Right, if I take a look at our picture from last time when we were talking about the different right triangles that we create when drawing an altitude inside of a right triangle, we ended up with these sides that we labeled A, B, C, D, E, F. Oh, I'm missing D. A, B, C, E, F. Okay, and here's something that's true. There's going to be two important relationships that are true using the altitude. So in this case, the first one says that the altitude, which we're calling C, so I'm going to rewrite this using the pieces. I'm going to say that the altitude, okay, is the geometric mean. So I'm going to put altitude here, okay, and altitude here. That the altitude is the geometric mean of the segments that were created when we drew in the altitude, right? So we had a hypotenuse here, a whole one segment hypotenuse. And when we drew in the altitude, we split it into two pieces. So I'm going to call this segment 1, okay, and segment 2, right? The segments of the hypotenuse. So that's really what C and E and F are labeling for us, but it's really saying that the altitude is the geometric mean of the segments of the hypotenuse, right? So if I take a look hiding down here at a problem that looks like this is a true right triangle, right? So if I bring it up a little bit, I can set this up and say the altitude is the geometric mean, which means the altitude is going to go in the two mean locations, which are here and here, okay, of the segments of the hypotenuse, which for us is 2 and 8. And if you notice, this is a true relationship. 2/4 and 4/8 both mean a half. And if I check it by cross multiplying, I get 16 and 16. So it works. It's true, right? So this is one of the important special relationships where the altitude is showing up. This is a proportion that we set up where the altitude is showing up in two spots. So it is the geometric mean, right? So we can look at the other one. It's a little bit more complex, right? So that one helps us find the legs and the altitude. And the question is, well, what if we don't know about the altitude, but maybe we know about the hypotenuse, or maybe we want to find about, something out about the legs, right? So there's all these different situations where maybe we don't know everything we need to know, right? So here's your other possibility, and it's saying that if we draw that altitude in, that the legs will be the geometric mean, and this is where you got to be careful, this is where it's tricky, of the entire hypotenuse, which we called E plus F, right? That's the whole hypotenuse, and the segment of that hypotenuse that is closer to the leg. So if you notice, my geometric mean was A, and the side that's closer to A, if I go right around the corner from A, I hit E. So that is the segment that is closer to A, and so I use that one. Whereas if I decided to instead use the other leg, instead of saying the leg A, I said the leg B, here's the only difference, right? Because I changed A to B, that's now my leg, I changed E to F. Because if I go around the corner from B, the segment that's closer is F, right? So we have to use the segment closer to the leg, and then an expression that represents the whole hypotenuse. So again, let's take a look at this example, right? And then we'll use these in the next video to do some problems using geometric mean, right? So if you notice, 2 is a leg, right? So I'm going to put that in my mean position. So I'm going to say 2 goes in both of the mean locations. That is the geometric mean of the segment that's closer to the leg, which for us is if I go right around the corner from 2, I hit the 1, okay? And the length of the whole hypotenuse, which we know they told us down here, is 4. And so if you notice, again, I get this true relationship that 1/2 is equal to 2/4, and so I have a true equality statement, so this proportion works, right? So we're going to actually keep going with this video. Okay, we only have a couple problems. So if you take a look at problems that look like this now, the whole point of doing all this geometric mean stuff and taking a look at these relationships is to be able to solve problems that look like this, right? So we're going to figure out what is the altitude, okay, of this right triangle, the big right triangle, and what is the leg. And the only thing we know is that the altitude cut our 16-inch or 16-unit long hypotenuse into a 4 and a 12. So we're going to use the rule about the altitude. It said that the altitude is the geometric mean. So let's start with that. We're not going to go any further. The altitude is the geometric mean, so I'm going to put that in both of these spots, of the segments that it created, right, when it cut the hypotenuse into pieces. So that would be the 4 and the 12. So I'm going to say that y squared has to be equal to 4 times 12. Well, 4 times 12 is 48, right? And then I can square root both sides, right? And I'm going to get y is equal to the square root of 48. And this, again, we're going to simplify our radicals. So I know that 48 has a 16 in it. So it's the square root of 16 would be 4 square root of 3, right? So I can figure out that the altitude in this case is 4 square root of 3. Right? And I could do the same thing with x. I'm going to have to use the other rule because remember, this rule only deals with altitude and hypotenuse, right? And this is not either of those things. X is not an altitude. It is not a hypotenuse. It is a leg. So the other rule said that the leg is the geometric mean, right? So I'm going to say leg is the geometric mean. So that's going to go in the mean spots of the segment of the hypotenuse that's closer to that leg, which for us, if we go right around the corner from x, I hit the 4. And the length of the entire hypotenuse, which for us is 4 and 12 put together, which we can just write as 16. Okay, so excuse me, if we add these together, I get x times x is x squared, and 4 times 16, which is 64. And if I square root both sides in this case, I get that x is equal to 8. So I can figure out that this leg has to be 8. And now we actually have enough information to find the third missing side. If I wanted to find this one as well, I could do the Pythagorean theorem, or I could use the rule here and do the same thing. Right? So our problem number 2 I'm going to skip because that is pretty much the same thing. Right? It's the same type of problem. Right? So we're going to take a look at one more example that is slightly more advanced with our algebra, okay, and it's this one right here, problem number 2, right? So if you notice what's going on here, if I were to try to set up the first problem and say, let's find the altitude, I'm going to say the altitude is the geometric mean, right? So I'm going to put that in the numerator and denominator of the two segments of the hypotenuse, which for us is 6 and x. And it's kind of like, uh-oh, we can't solve this problem because it has an x and it has a y. So this one's going to be a little bit more work. So we're going to actually have to kind of put a pause on this one. We'll say pause, can't do this one yet, right? And we're going to have to try the other one out and say, wait a second, I have this leg here. So let's try to set that up. The leg is the geometric mean, so I'm going to put that in the mean spots, of the closer segment, which is x, right? If I go right around the corner from 4, I hit x, of the closer segment, and the sum of those two segments, which is just the length of the hypotenuse, which for us is x plus 6. Right? So I'm going to say this is a true expression, and we can solve this one because it only has one variable in it. So let's do that. X times x plus 6 is x squared plus 6x, and if I multiply this way, I get 4 times 4, which is equal to 16. So I'm seeing a squared show up in my problem, and whenever a squared shows up, we usually want to set it equal to 0, because when it's set equal to 0, we might be able to factor, and if we can't factor, we can use the quadratic formula, right? And in either of those cases, we need a 0. Fortunately for us, this one does factor into x plus 8 and x minus 2. Okay, and I'm going to say this equals 0. And so if I set x plus 8 equal to 0, I get an answer of negative 8. And if I set 2 equal to 0, I get an answer of, of x minus 2 equal to 0, I get an answer of 2. Right, so I have two solutions, but let's go up and see if these make sense. If I plug in a negative 8 right here, that one doesn't make a whole lot of sense because I'm claiming that the length of this segment is a negative length, and that doesn't work. So I'm going to get rid of this one. Okay, so I'm going to say that the length of this segment is actually 2. So I'm going to actually fill that in right here. I'm going to get rid of x, and in its place I'm going to put a 2. Right, and so that helps us in our original problem. We can now unpause the first problem and say we can get rid of this, and we can also now get rid of x because I know that x is 2. So now I can solve this one and say y times y is y squared. 6 times 2 is 12. And so that means that y is equal to the square root of 12. And I can simplify this a little bit. We never want to leave our radicals unsimplified, and it's going to turn into 2 squared of 3. So 2 squared of 3. And so that would be my final answer. So I found x and y. So we had a little bit more work to do here. We had a problem that didn't work. We had a quadratic to solve and factor. We had to throw out an answer. We had to go back to our original problem and use all that information. So definitely a little bit trickier here, right? But not unreasonable. We know how to solve quadratics, and we know how to do these other things. So this is the basic concept. We have these two really important relationships that use geometric mean, right? And we're going to use those pieces to find any of the legs, any piece of the hypotenuse, or the altitude in a right triangle.